So sorry for the interruption. I have lost the connection due to the internet error and the power cut is there. So we are here in the Newton's law of cooling. So we are discussing that how the Newton's has found out the way to describe the mode of heat transfer, which is convection and which is far more complex than conduction and radiation in the mathematical terms. So we have taken an example that a hot cup of tea is placed on the table and after some time it loses its heat, or we can say that the temperature of the cup of tea will go down, okay, by the passing of time. But how this rate of heat transfer is related to time, that is discovered, or I can say that is mathematically formulated by Newton. Okay, so what does Newton says? The Newton's law of cooling statement, what is it is? Just a second. Statement. So it says that the rate of losing the heat is directly proportional to directly proportional to what? The difference of the difference of temperature of the system and surrounding. Okay. So this is the statement of Newton law of cooling. Mathematically, it is written as dq by dt is directly proportional to T minus T naught. Now, what is this T naught? So, T is the temperature of system, and T naught is the temperature of environment or surrounding. I will say temperature of surrounding because it is much more easier to understand in terms of system and surrounding. So, T naught is the temperature of surrounding. Okay. Now, if you remove this proportionality sign, dq by dt is equals to, you can say this k t minus t naught. Okay, this k is nothing but a constant and it is not thermal conductivity. Keep in mind. Okay, so this is equation number one. We will see. Now, we also know that the rate of heat transfer, the rate of heat transfer is also equals to dq by dt is equals to ka k into a dt by dx. Okay, this thing we also know. Now, if I equate these two equation, what do I have in mind? First equation, what will I have? Dq by dt is equals to k times t minus t naught. Okay, this is equation 1, and dq by dt is equals to ka. This k and this k is different. Ka t minus, sorry, dt by dx. Okay, this one is also we have, but the third one is also that we have is if you compare it, it will become k into a dt by dx is equals to k times t minus t naught. Got it? So from here you can say that, just a second. This dt by, oh, one thing, just a second. Instead of writing this dt by dx here, we will write that the heat transfer we also know is q is equals to mc dt. Okay, we also know that. Now if you differentiate this heat equation with respect to time, because this is something by which a body loses heat, okay, this equation, so it will become m into c dt by d small t. Now the second equation is this. Now if you compare it, it will become mc dt by d small t is equals to k into t minus t naught, and this k is also here the thermal conductivity. Sorry to mention that, thermal conductivity. Okay, and yes, so what we will do, we will take this mc in the denominator of this k upon mc. This k is capital here, t minus t naught dt by small dt. Now dt upon, take this temperature term below this differential temperature, which is t minus t naught is equals to k upon mc into dt. Now if you integrate it, and we will take this integration, not the definite one, it will be a indefinite integration. Okay, so 1 upon x dx results in ln x. So this will become ln t minus t naught equals to k upon mc is also constant into time t. Now k upon mc you can consider it to be a small k. Okay, plus another arbitrary constant we have taken ln a, let's say ln a. Okay, now you can say that ln t minus t naught is equals to this, you can write it as ln e raised to the power small k into t. Okay, because this ln is on base e, so kt will come in the front of this ln, and this ln e base e will cancel out and will become 1. So we can write this kt as ln e raised to the power kt plus ln a, we write in here. Now this will become ln t minus t naught equals to ln e, or I will write it as, because multiplication in logarithmic will result in product. So a into e raised to the power k into t. Now t is equals to t minus t naught. You can say here this is ln, ln and ln will cancel out. So it will become a e raised to the power kt. Now t is equals to t naught plus a into e raised to the power kt. Now this is something that we call Newton's law of cooling. Okay, this is the most general form of Newton law of cooling. Instead of that, you can also remember this equation, this one. Got it? So this is also considered to be the Newton law of Got it. So these two equation that we have, you can see in the equation directly here, to loosen up the temperature from T to T naught, what time it should take, you can calculate from directly from here. Got it? Now, we will discuss the emissive power and spectral emissive power. What is the emissive power? Before discussing that, okay, emissive power, if I talk about the emissive power, just a second. Yeah. Emissive power is the radiant energy emit by a body per unit time per unit time per degree Celsius per unit temperature. Okay, and the temperature should be in Kelvin for absolute value, and if it is given in degree Celsius, then you have to convert it into Kelvin. Okay, it is written as E. Okay, the unit of E will be joule energy, radiant energy per time per unit time, joule per second. ठीक है, joule per second per Kelvin. So joule per second will become watt. So it is watt per Kelvin. Okay. Now, what is spectral emissive power? Spectral spectral emissive power. Emissive power. Okay. So what is the spectral emissive power? It is the radiant energy. Same thing. Radiant energy just a second. Okay, so one mistake that we have did here, it is emissive power is the radiant energy per emitted by a body, emitted by a body per unit time per unit area, not temperature. Okay, that is the different thing. Area. So unit will be joule per second meter square or watt per meter square. Okay. Now spectral emissive power is, it is the same thing. Emissive power है, it is the radiant energy per unit time per unit area, but for a particular wavelength. Particular wavelength. So for a single wavelength, what energy a body is emitting for that particular wavelength, it is termed as the spectral emissive power. Wavelength. ठीक है. So it is defined as the E lambda. Okay, it is given by E lambda. So one of the relation you can remember in mind, that total emissive power is equals to integration of E lambda d lambda. Okay, so if you take the sum of all the possible values of spectral emissive power, then what do we have? You have the value of entire emissive power, complete emissive power by that body. Okay, so spectral is for one particular wavelength. Got it? It is also termed as, it is also termed as spectral radiant spectral radiant emittance. Okay, so this is it. Now if I talk about the absorptive power and spectral absorptive power, so absorptive power is the this one. It is the ratio of, it is the ratio of absorptive power it is the ratio of absorptive power to the total emissive emissive power emissive power. So generally it what it is, what it will tell you, that how much of the radiation is absorbed by a particular body within the this value of radiation which is fall on it. So how much it is able to absorb. Okay, so this thing is termed as what? This thing is termed as the absorptive power. Okay, so instead of absorptive power you can also say that it is the ratio of another thing, that is radiation absorbed or radiant energy absorbed. Radiant energy absorbed. Okay, and same thing mein, what is the spectral? So spectral is for one particular wavelength, so it is the ratio of absorbed radiant energy absorbed by a particular wavelength to the total emissive power of that particular wavelength. Okay, so spectral absorptive power is absorptive power. So it is the ratio of, it is the ratio of what? Radiant energy, radiant energy absorbed for a particular wavelength to the spectral emissive spectral emissive power or energy of that particular, that same wavelength. wavelength. So it is a dimensionless quantity because it is the ratio of energy by energy or power by power. So it is a dimensionless quantity. So we can define it is that in the spectral way, this A, the total absorptive power, is equals to integration of A lambda d lambda 0 to lambda. Okay, this is the relation. Now, if I talk about the Stephen Boltzmann law, for a perfect radiator of body, energy emitted per unit time is given by H is equals to A sigma T raised to the power 4, where sigma is the Stephen Boltzmann constant. Okay, where A is the area, T is the absolute temperature of the body, which is given in Kelvin, and sigma is the Stephen Boltzmann constant, which has a value of 5.67 10 raised to the power minus 8 watt per meter square per Kelvin raised to the power 4. So here you can say that the energy emitted is directly proportional to the fourth power of the absolute temperature. Now, this is for the perfect radiator body. But what if the body is not a perfect radiator? So we will use a term if only fraction of energy is radiated. So we will use the emissivity. This E is nothing but the emissivity. Okay, and emissivity tells us about the ability to radiate. Okay, so emissivity is defined as the radiant energy radiated by a energy radiated by a body to the energy emitted by energy radiated by, I will say it, radiated by a black body, because black body is a perfect radiator. So with respect to that, how much amount of energy this body is able to radiate is given by E. That is why E is always less than 1 for a body, for a practical body. Practical body. And E is equals to 1 for black body. So this E is the dimensionless quantity. For a perfect radiator, E is 1. Okay. Now, if the temperature is T, with the surrounding temperature is Ts, so this is the law of heat radiation. Okay. E sigma I T raised to the power 4 minus Ts raised to the power 4, where Ts the temperature of surrounding. Okay. So this is it from my side. Now, if you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive, and I hope you have enjoyed this session. Any kind of doubt, you are welcome to ask. Otherwise, you can leave the lecture. Thank you so much.